Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas. I know that when my colleague Marianne gets the midnight munchies, her favourite foods are, slightly weirdly, chocolate and mayonnaise. So you can imagine how happy she was that she had the chance to talk to Valerie Pinfield, Professor of Engineering at Loughborough University, who has used maths to work on both chocolate and mayonnaise. Marianne talked to Valerie at the Isaac Newton Institute for Mathematical Sciences in Cambridge, and you might hear some mathematicians in the background chatting over their coffee. They're part of the research program that Valerie is co-organising on the theory and applications of multiple wave scattering. As we'll find out, this has a huge range of applications, from understanding mayonnaise to making invisibility cloaks. While Valerie is a professor at the University of Loughborough now, her career path has also involved working in industry and time out for kids. So Marianne also asked her for some advice for women mathematicians and scientists wondering how to build their career. But first, let's start with the chocolate.
Now, Valerie, you work on mathematics and you've also worked at the chocolate makers Cadbury. So how do these things go together?
So I'll give you one example of the sort of work that I was doing there. So we were interested in how chocolate flows when you vibrate it. So this is liquid molten chocolate. And the way you make chocolates like a strawberry cream is to put the molten chocolate into a mould, turn it over and shake it to make the chocolate flow out, so that when you set it, you're then left with a nice thin shell of chocolate. And so what we were trying to find out was whether you should shake the moulds side to side or whether you should shake the moulds up and down to get the best result. And so that involved some mathematical modelling of the flow of chocolate, which is what we call a non-Newtonian fluid, which means its viscosity, or how easily it flows, depends on how quickly and how much you shear it, so you try and make it flow. So it's about how part of the liquid flows compared with its neighbours. So is it flowing at the same speed? Is it flowing at a faster speed than its neighbours? And so we built a model to look at the flow of chocolate with a free surface as well, you know, the interface with the air. And we were trying to find out whether side-to-side shaking would make a difference compared with up and down shaking when your flow is vertically, so the chocolate will flow out vertically. Unfortunately, the outcome of the model was the opposite to the outcome of the experimental work, so that's never a satisfactory finding.
So what do you do then?
Well, that means there's still more work to do, so we don't yet know the answer to that question.
So it's an unsolved problem in chocolate theory, whether you shake it up and down or left to right?
It was when I left Cadbury's, which was a long time ago, so that problem may have been solved since, but I'm not aware of the work there. So that's just one example as to how mathematics can help us with working with chocolate.
And what is the advantage of using a model rather than just experiment? Is it quicker, cheaper?
So I think using a model will help us to really understand and unpick the physics of what's happening in the system. So an experiment will often tell you what happened in your experimental setup, but might be more difficult to extend to a new system. Whereas if we do the modelling, we can say which of these physical processes is the most important in these particular situations and test them. So we can look at different conditions and do numerical experiments essentially over a wider range of conditions, and then we can design our process plant around those.
So it gives you a deeper insight?
Yes, I would say so.
Yeah. So, I mean, working for a chocolate maker is already very interesting, but generally you've had an interesting career path. Could you give us a quick summary?
Yeah, so I've done all sorts of things. My degree was originally in natural sciences, specialising in theoretical physics. And when I finished my degree, an academic career was not what I was looking for. So I went and worked for the Welding Institute, which is just outside Cambridge, now known as TWI, working on electron beam welding. So that was mostly modelling electromagnetic fields. And that's about joining metals, essentially, thick section metals. And then subsequent to that, I moved to Leeds and took a research post in the university there, and that was in a food science department, so a big move, but it sounded like an interesting thing to do, and that gave me also the opportunity to do a PhD there. And that's where I first started to work on wave scattering, which we'll talk about a little bit later, where we were using ultrasound to look at the properties of food emulsions and how stable those emulsions are. Can we keep them for a few months, or will they cream, for example, and the food will spoil if that happens.
What kind of food?
So you're talking about mayonnaises, milks of all different sorts. Those kind of oil and water mixtures was mostly what we were working on at that time. But you can also use the ultrasound to look at contamination. So fruit juices, have they been diluted or contaminated with something else? So quite an interesting way to apply ultrasound to interesting materials. And after that, I spent time in Birmingham, which was my time in Cadbury. So I was subject to what many people experience, which is the instability that comes with research contracts. So my research contract ended. I needed to find a new post. And I ended up at Cadbury's. I was very fortunate to get a post there, and it was a really fascinating job. I did all sorts of things. We've just talked about the mathematics, but I was doing kind of troubleshooting on the process plant, building and designing instruments, all sorts of things. So a really varied role there. And after that, I actually just took a career break. I started a family. And walked away from my career completely for a few years. But I did find it very difficult, the absence of the intellectual stimulation that I was used to. So I kind of was pulled back in. I initially started working part-time for my former PhD supervisor at Leeds. And that was part-time and remote working, which back in those days was more unusual than it is now. And just gradually increased the work that I was doing there, moving to Nottingham University later. And during that period, I was doing the childcare. I wasn't travelling an awful lot, didn't go to many conferences, but carried on publishing and doing that high-quality academic research, and eventually took a full-time academic post as a lecturer at Loughborough, and by which time I was in my early 40s, so a bit of catching up to do in terms of the academic career route, but I've been there for over 10 years now, and I'm an established academic now working in a chemical engineering department.
So lots of different
Yes.
things you've done. So taking time out for children and then coming back is something that many would consider as a brave step, and something that worries, especially women mathematicians or women scientists. What advice would you give to an early career researcher who's thinking about all these things and how to combine family and career?
Yeah, it continues to be a challenge, doesn't it? And I think you have to find a solution that works for your personal situation. I think there's a great deal of instability in the academic world. But I would encourage people to think that academia is not the only place to work, and that you can follow your nose and do lots of interesting things. And, your career route doesn't have to follow a very linear path, which is, a conventional path. You can actually divert and do all sorts of different things. So I think just, follow the interest, follow your motivations, and find something that you enjoy doing, and that might be different at different stages of your career.
So don't necessarily stick to the prescribed path, and don't be afraid of taking detours.
Absolutely, yeah. I think taking a risk sometimes can also work. It can be brave, but sometimes just taking that little bit of a risk, taking something that you're not sure whether you can do that, but actually go and give it a go and give it a try. That can lead to a fascinating career.
Interesting. Yeah. And you're now doing something very academic, which is like you're co-organizing a research program at the Newton Institute where we are right now, which is about multiple wave scattering.
Yes.
So what is that about? And maybe if you give an example, maybe you could use the mayonnaise or something to give us an idea of what that area of maths is about.
Yes, okay, so waves, we're used to waves in all sorts of forms, so optical, so light waves, sound waves, we're using sound waves now to talk to you. Water waves, so waves on the ocean, these are all different sorts of waveforms, and they interact with objects in their path. And when they interact, they can scatter new waves off those objects. So multiple wave scattering is interested in how all of those waves from all the different objects interact with each other and what is the overall outcome of that. So the multiple wave scattering is absolutely fascinating and occurs in all sorts of different fields. So for example, imaging of cells and tissues is using scattering of the electromagnetic waves. X-rays, another imaging for tissues, human tissue, you'll be familiar with that. Noise cancellation technology, that's then sound waves. How can you create a medium in which the scattered waves result in cancelling out the noise that you would otherwise have heard? So many of us would be using noise cancelling headphones, and that's the wave technology in there. On the mayonnaise example, so let's go back to the ultrasound. So these are sound waves, but you can't hear them. They're higher frequency, shorter wavelength. And so those waves are travelling through the mayonnaise. We can transmit a wave through them, and it will bounce off all of the different particles, and the waves bounce around between all of the particles. And the overall result of that is a perceived loss of energy in the wave as it travels through the material. And by looking at that loss of energy as a function of frequency, that's a spectroscopy technique, we can then work out things like what's the concentration of particles, what is the density of particles, what is the size of the particles. So that allows us to detect something about the properties of that material.
So it's detective work. You kind of look at what happens to waves, and from that you deduce what's happening inside the mayonnaise or inside a person's body.
Yes, that's right. So that's one way to use the waves, and that's the way that I'm most familiar with. Now people are designing materials to make the waves do something. So to design a structured material so that waves will follow a particular path through that material. And this is how you can construct, for example, an invisibility cloak, which is the one everyone's excited about. So that's using the optical wave scattering to make the waves travel in such a way that you can't actually tell that there was an object there. After all, you've cloaked it.
So have we got, does this exist? Do we have invisibility?
It does exist, yes. You can make a material that does that.
Who uses that? The army? Or
Well, of course, yes. There are lots of defence applications in these metamaterial areas, in acoustics to do with hiding your submarine, hiding things from radar and so on, yes.
Okay. And so it's a research program, a 6-month-long research program here at the INI, focusing on the mathematics. So what challenges are there that need to be solved still?
So one of the purposes of the program is really to bring people together working in different application areas and with different mathematical methods. So what we wanted to do was bring those people together to share and sort of cross-transfer techniques that might be useful to solve different problems. So you can take a look at some of the techniques that we're using on the webpage for the program, and on the video that we put together about the program. But really it's about that cross-fertilisation of ideas to get those mathematical techniques working in the best possible way to solve the problems that still remain and see what we can do. We need to expand our ideas as well as to what is possible in the wave area, as well as solving the problems that we already know about.
Yeah. And somebody listening and thinking about the mathematics of waves, they might remember from school sine waves. for
Yes,
example.
yes,
Sine
yes.
things. Do those concepts play a role?
Oh, they really do, yes. So sine waves are a really comfortable place for us to work. So a sine wave is really representing a single frequency. So many of the analyses that we do, we will look at a single frequency and then we might combine many frequencies together in order to look at more realistic signals. But certainly we will pick out those single frequency sine waves and do our analysis based on that waveform before we make things even more complicated.
Okay. And what's it like running such a research program here at the Newton Institute?
So I think the benefit of the extended research program is the time that you can spend with other researchers and the range of researchers that you can bring together. So I think one of the aspects of the program that I've most enjoyed is that it's been so intellectually stimulating, just to be surrounded by people working in wave scattering and sharing approaches, techniques, ideas. And it means that as a researcher, you know, I'm coming away with many ideas of things I want to do in the future and people that I can work with. And so that just bringing people together and allowing us to spend that time talking, discussing, interacting really does help to accelerate the research field.
Mm. And are you planning another career change?
Not quite yet, I don't think. But, you know, I've always got something in mind. There might be something really interesting out there that I need to do.
Okay.
Who knows?
Exactly, who knows? Well, thank you very much.
A real pleasure. Thank you.
That's it for this episode of Maths on the Move. To find out more about Valerie's research programme at the Newton Institute, go to newton.ac.uk/event/MWS. And to find out more about the maths of waves, go to plus.maths.org and search for waves. Thanks for listening and bye-bye for now.